Hey everyone, today we'll be recreating NeRF using PyTorch, and this will be mainly focusing on the encoding and model portion. If you haven't already read the paper, I definitely suggest that you do. I'll go over some of the details, but not all of them. And this notebook kind of takes after the tiny NeRF implementation that the original authors wrote, which you can find here. This is in TensorFlow. I just have everything in PyTorch. So NeRF, neural radiance fields, is just a way of representing a 3D scene using a neural network. So you can take in a 3D position, XYZ, and a camera view angle, theta phi, and feed it into the network, and it can output the color and density, RGB and sigma, for the scene at that specific vantage point, essentially. And this way, if you feed it multiple images to train on, the network can generalize and render scenes from views it hasn't seen before. And so what it does is you get the RGB sigma values for a bunch of points along a ray that's casted from your vantage point into each pixel in the scene. And they use volume rendering to get the final pixel image. And because volume rendering is differentiable, you can calculate a loss based on the image it renders. And you get that loss by comparing the rendered image to the ground truth, and you can use that loss to adjust your network weights. So I'll just be going into a little more detail on the encoding portion and the model. So you have your imports, and this is your data, so make sure we load that. And this is the architecture and encoding equation straight from the paper. These green blocks are the encoding, so the network will, this is the position encoding and this is the view encoding. And so the network takes in the position encoding. Each of these solid black arrows is a linear layer with a ReLU activation function, and we have a few layers of those. We have a skip connection where the position embedding gets added back in, and we get to this layer here, and it's two sets of weights, one which maps straight to the sigma value of density, and the other which goes straight to the other linear layer. There's no activation function because it's an orange arrow. And we also can concatenate the view encoding. And finally, we get to the last layer, which is mapping to the RGB. The dotted line means it's a sigmoid activation. So this is the encoding equation, and the reason we have an encoding such as this is we need to be able to capture the fine details in a scene. So things like quick changes in texture or lighting. And the authors, the way they decide to do that is by mapping a 3-element vector. So for example, XYZ for your 3D position, or in the case of the view vector, you won't have angles. You have a unit vector. So it's also 3 elements. So their rationale is instead of trying to estimate these high-level fine features with just XYZ, you can cast them into a higher frequency representation by using this encoding. So that way you have L frequency bands that you use, and the higher ones are able to capture high frequency features in the scene better than these lower ones. So in the case of the paper, the authors use L equals 10 for the position encoding and L equals 4 for the view encoding. So let's just write the encoding equation real quick. We have an input tensor X, and our level, frequency level, will set default L. We'll make an empty list, which is our result, And for each frequency level and for each function, we want to calculate that function and append it to the result. So we'll do res.append the function, and the function here is 2 to the current level times pi times p. So in this case, p is our input vector. And then we want to return the concatenation of all these vectors and tensors inside the list. So let's try that out. So if you have a 3-element tensor and you are using 10 levels of 10 frequency bands, you would expect a shape of 60, because for each frequency band you have 2 outputs, sine and cosine, so it's 10 times 2 times 3, 60. Alright, so now that we've done that, we can move on to building the actual network. So first we'll want to initialize, and there's a few arguments we'll take in when we create this network. We'll take in our position encoding dimension, which is 60, our view encoding dimension, and then our hidden layers, which is 256. So there's 2 parts here. One, in this section, we'll make all of our layers, and then we have to use the forward function to use them. So we can split this architecture up into a few parts. So you have a linear that goes from the encoding to hidden dimension, and then you have 4 layers of just linear ReLUs in a row. Then you have your skip linear, I'd call it, because it's the linear that happens right after your skip connection. And then you have 2 more layers of just linear ReLU. This one is, you'll have one mapping to density and one going to the next layer. And finally you have 2 color layers. That's what I'll call it. So let's make the first one, which is linear 1, and I'll be using NN sequential a lot because we're always doing a linear followed by a ReLU. That's the first one, and then now we want to go to the linears that are before the skip. And so for this, I'll just append 4 straight. All right. So now we're here, and we've just concatenated the skip connection. So we need to make one called linear skip. And this one will be essentially the same as this, except our input dimension will be the position encoding dimension plus the hidden dimension. And now we have two layers, 1, 2, right after the skip, so we'll call this post skip linear. And this is going to be similar to this one. Except we only have two of them, and we want to make sure we append to the proper one. Okay, so now we've gotten to this portion. We need one that maps from the density. We'll call that density layer. Sequential. So we have one linear that goes from hidden dimension to 1. And we need to use a ReLU here because the density can't be negative. Spell density right. And now we have just a linear without any activation. We'll just call it linear 2. And now we have two color layers, one which is going from the hidden plus view encoding to 128, just half of the hidden, and then one that goes from that to the RGB and uses a sigmoid. So we'll do self color and this one goes to the color RGB, and we want to use a sigmoid. Great, so now we have all of our layers, and we just need to implement the forward function now. So the input will actually be the last dimension will have 6. So we want to extract the positions and the view directions from this. So we'll have batch dimensions and samples. We only really care about the last dimension. So the first 3 will be positions, the last 3 will be view directions. Then we'll do the encoding. So and then we'll compute the first linear layers here all the way till here. And then next we want to add the skip connection. So we'll do a concatenation. And then we'll do the linear layer right after that. And then the 2 linear layers after the skip. And now we're at this point, we can do the density prediction. And we can also go on to the next layer. So now we are here. We need to concatenate the view encoding and then do these next two color layers. So we'll do concatenate. Then we'll do the first color layer. And then our RGB will be this output from the second color layer. And we want to return a concatenation of the sigma and RGB. So that is the entire network and encoding from the paper. We can run here, and these are some functions that were just translated straight to PyTorch from their notebook. All it really does is it's getting arrays, it's generating arrays for a certain camera configuration, and then sampling points along these arrays so that you can feed it into the network and get predictions. And once it gets those RGB sigma predictions, it renders it into a RGB map, which is the image that we compare to the ground truth. So I've already run the training loop as well, and so this is kind of the training progression you should expect. The PSNR is peak signal to noise ratio. It is essentially measuring how well you're recreating the view compared to the ground truth. So you want this number to keep going higher. And these are some functions which allow you to visualize and actually see it being rendered from all these, essentially a 360 view. And what I'll do is I'll just run this to make sure our model works. And you can usually tell something's wrong within the first 50 iterations if the PSNR number doesn't really improve much. Okay, so I can tell just from this that it's working. Definitely go back and you can change these numbers and test out different types of configurations to see if some work better than the others. Typically, if you have more hidden layers, you're able to estimate, you're able to better render the scene in fewer iterations, but it will take longer to train. So those are the kind of trade-offs you need to make. And we'll just do one more. Okay, so this looks like it's fine. Thank you for watching, and hopefully this was helpful if you're new to NeRF.